explain something that came from joint work with Steinberg and with Randal-Williams that relates many of the characters that came up at the end of the last talk to constructions in sort of abstract homology theory. So I know there's like a wide mathematical culture here, and so the first talk and maybe half of the second talk is going to be quite abstract, but then the goal is to explain how you get like quite concrete descriptions of these abstractly defined things, and then how it ends up being, in the specific example, described in terms of this sort of pre-block group and things of that nature. But the beginning will necessarily be a little abstract. So the goal, somehow, is to exploit the multiplicative structure on the homology of GLN of some wing F, probably a field, but not a single n at a time, but sort of all of them at once. And here, let me say F is a ring. It will usually be a field or a PID. So everything I say will be legally true for fields or PIDs, and it will be morally true for things like a bit bigger, like Dedekind domains and so on, with a few modifications. And there's an implicit field of coefficients as well that I will leave out of the notation. Let me say with a field that will be called K if it ever needs to be mentioned, of coefficients. And what does multiplicative mean? It refers to the fact that when we do all general linear groups at once, we can take block sum of matrices. You can take an n by n matrix and an m by m matrix. You can take their block sum, and you get an n plus m squared matrix. So let me start with that. So block sum gives homomorphisms GLN of f, GLMF to GLN plus m f. And this endows the collection of all the homology groups with a multiplication. With an associative multiplication. And it's associative because block sum of matrices is literally associative, right? And that makes it into a bigraded wing. Right? It's graded by homological degree and also by this symbol n. So bigraded. But it has more structure than that. Sorry, before I talk about more structure, in particular, there's an element that won't show up very much, but when it does, it will be called sigma, and it's just the generator, the canonical zero-dimensional homology class of GL1. Like the generator. And we can think about using this multiplication, left multiplication by that element. And that gives a map from the dth homology of GLN minus 1 to the dth homology of GLN. And this business called homological stability is the question of, is it the case that these maps are isomorphisms when we fix a D and let n be large compared to D, let's say. So this business called homological stability equals, is this map iso, let's say for n large compared to D, which typically large means in some quantitative sense like 2D or something like that. So that was actually the sort of motivation for thinking about the kinds of things I'm telling you about, but it turns out that it's kind of interesting even if you're not particularly interested in this homological stability phenomenon. Yes?
Block sum.
Yep.
It's not the same block as in his talk, right?
This is a K. I want to talk about a bit more structure that you get in this situation, which comes from the fact that block sum is, in some sense, commutative. In a very real sense, it's not commutative. If I take the sum of two block matrices in BA, they're not the same matrix, but they're canonically conjugate. And the way to talk about that in slightly more adult terms is I want to consider the groupoid fancy G, which is just all the GLNs at once. So it's the groupoid whose objects are just natural numbers, and whose morphisms are, there are only endomorphisms, and they're given by GLN. So the morphisms from n to n are GLN, and the morphisms from n to anything else are empty. Another way of saying this in more conceptual terms is it's just the groupoid of finite dimensional F modules and isomorphisms between them. Okay. I mean, there are other morphisms that we don't take, which are the non-isomorphisms. I just want to consider the groupoid. And when you think about it this way, it's very natural to observe that this has a monoidal structure given by direct sum of vector spaces, and that it's in fact a symmetric monoidal structure. So let me just say this is symmetric monoidal via and that's the grown-up way of saying block sum of matrices is commutative in some sense. The symmetric monoidality for block sum is exactly the conjugation you need to write the block sum AB as the block sum BA. But being symmetric monoidal is like a quite strong and good structure. Here's one thing you can do with it. So in particular, I can think about making a maybe k-fold sum. Gives me a map from k copies of the Cartesian product of k copies of the groupoid to the groupoid just by adding everything up. But the result I get somehow doesn't depend on the order of the inputs. That's what it means to be symmetric monoidal and not just monoidal. And one way to express that is that it extends to a functor from what you might call that. So here, by E sigma k, I mean the translation groupoid of sigma k acting on itself. So it's the thing whose object is sigma k and whose it's just the translation groupoid of sigma k acting on itself. That's what it is. Like what you might call sigma k mod sigma k. And that, as a category, is contractible. It's equivalent to the category with one object. Because every object is, like the name of the object is the name of the morphism you need to send that object to the identity. So this is just like a categorical version of like the Borel construction, when you have a group acting on a space and you force the action to be free by crossing it with a big contractible thing that has a free action. It's just a categorical version of that. And so this is a functor, and so we can take nerves of these categories, and we can take cellular chains of the nerves, and that gives us some map of chain complexes. So taking nerve, then cellular chains, and using some monoidality of cellular chains, and putting them all together as I vary over k, we get something that I'll write like this. Chains on this groupoid to the tensor k, and chains. Okay? And chains on the groupoid just means it's exactly the object I'm thinking about. It's the direct sum n from 0 to infinity of group chains of the GLN maps. So this is some way of saying that there's a commutative, in some sense, multiplication on chains on the in this groupoid. This thing here just means the chains on the nerve of this groupoid. It is an algebraic E star G for this group, so it's a resolution of the trivial G model. And this whole gadget here is, for now, this is just notation, and then I'll explain the meaning for the notation in a moment. This is obviously some construction you could do given any chain complex, which in this case is C star G. You could just write down the same formal symbols with any chain complex. It probably wouldn't have a map back to itself, probably, but you could write down the left-hand side. So these E star sigma k's are an example of an operad. It's called the Barrett-Eccles operad, but let me just say what it means. There are maps. If I take the one for k, and then I take k other ones. So I take E star sigma n1 up to E star sigma nk. Then there's a map to E star sigma n1 plus sub nk. And this just corresponds to the fact that if I give you a permutation of k things and then k permutations, I can plug those k permutations into, it's like block sum of permutations. That's what it's given by, yes, block sum of permutations. And times, of course, means tensor. And let me just say, which are suitably equivariant and associative. Meaning if I try to compose this with k many operations acting on this and get some enormous composition, then the two ways of making sense of that are just equal. And what that implies is that if I look about this construction, this left-hand side, and do it to itself on some chain complex, it has a canonical map back to one copy of itself. Okay, which is just given by using all these maps to do in various components. And that's what it means to say this E infinity plus is a monad. So it's a functor that has a map from its, it's like a monoid in endofunctors. It has a map from its square back to itself. And I guess it has a map from the chain complex itself maps in as the k equals 1 component. So it has a kind of unit as well. And this tells us what an E infinity algebra is. So a unital E infinity algebra is a chain complex X, let's say, with a map it's exactly what we have here, in fact. It's a map from infinity plus of x back to itself that somehow tells you a way of multiplying together arbitrarily many things in x to get something in x again.
Oscar,
Yeah?
what does plus mean?
Plus is the, yeah, it's the fact that it's unital everywhere. And it will always be unital, and I will always write plus. If you want to do non-unital things, then you don't write a plus, and I will endeavor not to do that And there's a condition which is, let me just draw it once. If I do E infinity of x, there are two ways you can get to E infinity of x. Let me give these some names. This is called like alpha for action, and this is called mu for multiplication. And on here there are two things you can do. You can use the fact that E infinity is a monad to get to there, and that has nothing to do with x. And then you can use the action. Or you can use E infinity plus of the action, and then use the action again. And these are literally equal. That's what it means to be E infinity algebra. This corresponds to like associativity of a group action on an object or something like that. And let me just say the above shows that chains on the groupoid has this structure.
Sorry, could you maybe spell out again what it means to take E infinity plus of the action?
I mean, alpha is a chain map, and E infinity plus is a functor. So it's just the map induced by alpha on that functor. So if I have a map just between any two chain complexes, the fact that the domain one happens to be called E infinity of something is irrelevant. If I have a map to any two chain complexes, F, then I get a map between these just by doing tensor powers of F in the different submaps.
Think X is a group and replace E infinity with like the free group functor, and then then write down a diagram, and then it'll be similar.
Say again. Say
Yeah.
again the question.
Maybe if you shove out the lower board a little
Maybe I
bit.
just
you see
wanted what it
is
was on the lower board. Maybe this was more. I mean,
plug in and for
every of the.
So it's somehow irrelevant what this is or the tensor power is. I just have a map between chain complexes. It induces a map of all tensor powers,
Yeah.
and then I can tensor with a fixed thing. Is that okay for now? So, right. So, my claim is that being an E-infinity algebra is some kind of fancy, elaborate structure on the object, and we ought to be able to extract unfancy structures from it that are sort of down to earth and that we can think about. So here are some basic consequences. So the first one is the following. So I have k equals 2 piece of this structure. That's part of the data that I have. And I can map to it from the thing where I don't take the quotient. And now this E star sigma 2 is just a resolution of the trivial module. So this is just homotop equivalent to just not having it there at all. And at the level of homology, this gives me a multiplication on the homology of G. I use the inverse of this chain homotop equivalent, and then I just do all these maps. So this induces a multiplication, and this is just the block sum multiplication. But when you write it this way, you see something additional, which is that, of course, this map, if I swap the two factors and then do the map, is literally equal to doing the map without swapping the two factors, because I've taken the quotient by the sigma 2 action. So that shows that this is invariant under interchanging the two factors. And what that means is that the block sum map is commutative, not just associative. And the only subtlety is that in chain complexes, whenever you swap factors, you use the Cazor's sign rule, that AB is minus 1 to the degree of A times the degree of B times BA. So, so the fact that it extends over E sigma 2 tensor sigma 2 something implies that this is graded commutative. Okay. So that's one consequence of having a E infinity structure and not just a multiplication, is that it forces it to be commutative in the graded sense. So there's one less basic consequence that won't play a major role, but I want to explain it a little bit because it somehow gives an idea of what additional information this E infinity structure is telling you. So a less basic consequence and for this we should work with FP coefficients, so over a finite field, which is, suppose we have a homology class, say of some degree D, on this groupoid with FP coefficients, specifically. Okay. So X is meant to be the name of the cycle that represents the homology class X. Then here's something we can do, and I'll develop it from right to left again as before. I now want to use the p-fold, the p component of this, so the one that has to do with the p tensor power. And I want to use that. What is a cycle? What does it mean to give a cycle in a chain complex? It means to give a chain map from the chain complex, which is just fp in degree d. That's what a cycle is. And by functionality of this construction, I can just put fp in degree d, take its pth tensor power, and then this is the map induced by the pth tensor power of the chain map x. Okay. So for this, I should pick an actual cycle representing the homology class. And now this side is just some chain complex that only has to do with the symmetric group on p letters, and you can just calculate what its homology is. And the point is that any universally defined homology class in that object gives you some kind of derived homology classes depending on x in the homology of G. So how do I want to say that? It doesn't take forever. So any element of the homology of the left-hand side, so I've written it as some complicated construction in chain complexes, but if we think about what it means, this is just group homology of sigma p with coefficients in the pth tensor power of a one-dimensional vector space, and that is just a one-dimensional vector space. And the only subtlety is if that D is odd, then the permutation action has a sign involved. If D is even, it doesn't. So basically, it's FP with a sign action or the trivial action, depending on the parity of D. And sort of shifted up by PD many degrees. But if you pick any such homology, and this you can just calculate, okay?
Sorry, Oscar, when you write FP brackets D squared is 0, is that what you mean? Or?
No, D is the degree in which I...
Oh, D is a degree. Oh, D is a degree. Okay, yeah, sorry.
So I started with the D homology class.
Oh, yeah, right.
So FPD is just... So this kind of square bracket shift just means shifting the grading of, I mean suspension and desuspension and so on. So any element of any cycle in here, I can think about as a map from fp, whatever its degree is, into there. And the composite gives me some new homology class in G that depends on the x that I started with. So it gives a class in the homology of G with fp coefficients derived, let's just say, from x. And these are known as, they're called Q1, Q2, and so on. It involves knowing what the calculation of this is, which I don't want to go into, but one can calculate it. They're called Qi, and they're called didactic equations.
Could be a beta too, right?
Yeah.
Can be a beta.
Yeah, there's also, yes, you can also compose it with box stones and things like that. B equals to the epsilon, e to the epsilon. It's not very important for what I want to say, it's just to give some idea of what additional structure you get on the homology of a thing when that thing is an infinity algebra. And the first bit of structure is true of any ring of coefficients. The second bit of structure is specific to fp, to finite coefficients. So if you're used to working rationally, you've probably never heard of this kind of structure, and that's because there is no such structure if you work rationally. An example to give you an idea of if p is 2, I talked about this element sigma, which is the generator of H0 of GL1. And if you think about how the degrees work, this Q1 will be H1 of GL2 of the field with F2 coefficients. And it is exactly the matrix, or it's the homology class represented by the matrix 0, 1, 1, 0. So it's typically not trivial. Somehow remembering the fact that sigma times sigma, there's a symmetry, gives you a reason why sigma times sigma is homotopic to sigma times sigma. But because sigma times sigma is already equal to sigma times sigma, giving a homotopy from it to itself is the same as giving a one cycle. And that's what this one cycle is. So that somehow gives you an idea of the flavor. So there's one more bit of structure which I've already implicitly used, which is that this object G, its homology groups are bi-graded. They're graded by homological degree, but also by the n in GLN. So let me put that here. So some further structure. Chains on G, or its homology, canonically comes to us as a graded object. Graded by the natural numbers. So the whole structure you get is it's a natural numbers graded infinity algebra. And there's one very final piece of extra structure, which is that because it's graded, you can always project to the grading 0 piece. And you can always just use the fact that GL0 is the trivial group. So it comes with canonical augmentation. Which will be called epsilon. It goes from this to just whatever the field of coefficients is, thought of as being in bi-grading 0, 0. So it's in homological degree 0, and it's in natural numbers grading 0. So that is the kind of structure I want to work with. And the view I want to take, okay, so doing anything very serious with these is very complicated. The view I want to take is an infinity algebra is just like a commutative ring in some category. So what we're working with is an object that's like a graded, augmented commutative ring in some fancy setting. And I just want to do things with it that you will naturally do if you had a graded commutative ring with an alternative. Okay. And how you actually implement the things I want to do in this framework, I will not dwell on. But they all can be implemented, and they can be implemented in all sorts of different settings. All sorts of different foundations is what I mean.
Would it be hard to give an example for H3 of GL2F to compare with Clément's? So he.
So that's going to. So that a lot of that will show up in my third talk, but not immediately. Yes.
Bigger foundations to use, which one would you
As
recommend?
of today, you can just do everything infinity categorically, and you will have a very easy life. I wish we had done that 7 years ago, because we wrote a very long paper not doing it that way. So that's sort of how I'll describe it in these lectures, in a kind of synthetic infinity categorical way, meaning just believe that everything works out. So here are some easy constructions one can do. So the first one is the category of things I've just described. So you look at chain complexes over K, field. You look at natural numbers graded objects in chain complexes over K, and then you take augmented E infinity algebras in that category. So an object of this category is exactly the kind of datum I just described. And on the other hand, we can just take the kind of underlying thing, which is just a natural numbers graded chain complex. And one thing you can do is just forget the structure that you had. So forget all the multiplicative structure. I want to do this I want to do not the completely naive way of forgetting. Namely, I want to say if I have such a thing, and its augmentation is called epsilon, I don't just want to remember A as a graded vector space, I want to take the augmentation ideal. So that will normally be called A+, and it means the fiber of the augmentation. Okay? In fiber in chain, i.e. kernel. So that's one thing you can do, which is roughly forgetting the multiplicative structure. There's another thing you can do, which goes the other way. So if I just have any chain complex, any natural numbers graded chain complex, I can make an algebraic, an infinity algebra in this category in the following way. I can't just send it to X. Let me just write the answer. I send it to the sort of unitization of X, where K is a unit, and whenever I multiply any two things in X, I get 0, using any of these fancy multiplications. So this is like the square 0 ring given by a module X. So this is the square 0 on X. So when I multiply 1 by anything, it acts as a unit, but when I multiply any two things in X, I just get 0. So these are two elementary constructions in the sense that you can write down a formula for what they do. One lesson I've learned from having to think about these things higher categorically and so on is that it's not a good idea to make all your definitions be given by formulas. It's a good idea to make all your definitions be given by what they are supposed to achieve, and then later work out a formula, if you need to, for what that thing is. Because it's very difficult in this infinity land or sort of homotopy coherent mathematics to write down literal formulas that will literally satisfy sort of identities up to homotopy. It's so difficult that you can essentially never do it. So what the pattern will be in the rest of this talk and the next one is that I'll define certain things very abstractly, and then we will use their abstract properties to derive formulas for them, and they will be somewhat familiar formulas. But you could never use the formulas to define them in any sort of coherent way. So here that goes as follows. One checks that these preserve all limits. Sense of category theory, so if you take a limit here and then apply the functor, you'll compute the limit in that band and so on. And a functor that preserves all limits, barring some set theoretic issues, has a left adjoint.
Let's jog over there.
So have left adjoints, which are called in the two cases F and Q. And they go the other way, of course, and I won't write out the source and target again because I will spend ages. How should you think of what these functors are doing? If you look at the map that forgets the algebraic structure, what would this do in ordinary algebra? If I look at the functor that forgets the multiplication and then look at its left adjoint, it just makes the free object on that. So f of x is the free augmented unit or infinity algebra generated by x. And all you know about such a thing is that if I want to give a map of augmented unit or infinity algebras out of it, I just have to give an ordinary map out of x. That's all we know about the thing, basically. In fact, the way I've set things up, we know a little bit more. Namely, it is just this thing that I was calling that. What about Q? Maybe this is less familiar. In ordinary algebra, if you just take the map that takes an abelian group and sends it to the square zero ring, so you take Z plus whatever the abelian group is, and you make it into a ring in the dumbest possible way, what is the left adjoint of that? It's the functor that divides out all multiplications, all proper multiplications. It's indecomposables. And that's what Q is as well. Tautologically. Right, I'm defining this to mean what indecomposables must mean. So let's just say indecomposables, not a base bit of an algebra, indecomposables of A morally is like A modulo all products of things in the augmentation ideal. Obviously, you don't kill 1 times elements. You only kill proper products of elements. So 2 things in the augmentation ideal. So it's very uncomfortable at first because you think, like, oh, well, what is the second group in this chain complex? Like, how do I think about that? Like, you just don't ask those kind of questions. all you know about this object is that maps into it is the same as maps from the zero algebra, from the thing considered a zero algebra, and so on. Okay, out of it, sorry. That's all we know about it for now. You can get some easy consequences as follows. So here's an obvious construction. If I take an object x, consider it to be infinity algebra by this zero kind of construction, and then take the underlying object again. That's just literally the identity. You can just observe in the formulas. You take x, you take k plus x, and then I take the augmentation ideal of k plus x. Well, that gets rid of the k again. So this is just x. And that's somehow natural in x. In other words, this is just the identity. And a little bit of category theory yoga says when you have 2 functors that satisfy some equation, and they both have left adjoints, then all their left adjoints satisfy the same equation. And what that tells us here is that Q composed with F is the identity. In other words, for spelling it out, if I take the free E infinity algebra on X, then I do know what this Q construction does to it. It just gives me X back. It tells me what the generators were of the free thing that I had. Okay? Out the generators. And obviously this is a bit of a dangerous way to say it, right? Because if I give you a group, for example, and I promise you that it is a free group, you can't pick the generators. That's not a meaningful statement. What you can do is you can take the quotient where you kill all non-generators. And that's what this is really telling you. It's not really giving you the sub-object x, it's giving you the quotient x, which is when you kill all x squared and x cubed and things like that.
In your formula for the square zero extension?
Yeah.
Oh, sorry. I thought that was R. Is that K?
I don't know what R would be.
Okay, that's K.
Yeah, it's the yes. It's just the ground field that we're working over. So using this, you can calculate Q on some kinds of objects, as long as they're described to you in a quite abstract way. If it's described to you in a quite abstract way, then you can evaluate quite abstract constructions on it. The difficulty is working with things like chains on G, which is not described in an abstract way, it's described in a concrete way. But I first want to explain what you can do if things are described in an abstract way. So if A is an augmented infinity algebra, and suppose I have a homology class, graded as well. Suppose I have a homology class in some bi-degree of the augmentation ideal. Okay, and I didn't comment on how I index things, but I write the grading first and then the homological degree. That's how I'm always going to index things. Then here's something you can do. You can start with X, which is a map from the chain complex, which is K supported in bigrading ND, to A bar. That's what X is. By definition, it's a chain map like that. I can observe that this side is U of A. By my definition of U of A was take the augmentation ideal. But that means by adjunction, U had a left adjoint, which was called F. So this, a map like that, is exactly the same data as a map of infinity algebras, which I'll also call S, from the free one on the left-hand side to the right-hand side. Just the same data. That's using that this free was left adjoint to U. Now this has an augmentation, and I can just make the push out in natural numbers graded, uniformly augmented infinity algebra. And everything I know about that object is that it's the push out of this diagram. That is the complete description of this object somehow. So I can make the push out, which I normally call something like A union along X with, I might call it something like that. And I think about it as attaching n comma d plus 1 cell to A. Right? If I made the push out here, that would exactly be attaching an n comma d plus 1 cell to this chain complex. But I'm doing it in algebras. So I'm attaching a cell in the land of infinity algebras to this object. And by definition, that just is this push out. By definition. I don't know very much about this other than the push out. For example, I know that the homology class X will become 0 in here. But that will have all sorts of consequences for the other homology of A. For example, if I kill X as an infinity algebra, then all these dilateral operations have to also die because they're defined using the infinity algebra structure. So it will have some catastrophic effect on the actual homology of A. But at the chain level, it's just given by this push out. And now, I can apply Q to this push out square. And Q is a left adjoint, so it preserves the colimits. So now I just get and on this object it just gives me what I had before. On A it gives me Q of A, whatever that is. Q of the thing with no generators is just 0. And Q of that is whatever the push out of this square is. This is just a push out in ordinary chain complexes, maybe with an additional grading. Okay, and the lesson is that attaching an E infinity cell to A has a very simple consequence on this Q construction. It just attaches an ordinary ordinary chain complex cell to Q.
Push out is a short exact sequence now?
Yes, I mean maybe you could make this be an inclusion and things like that if you want to.
Automatically from being a push out, right?
I mean, everything is in some derived sense where you can't not be a short exact sequence. Yes, that's the mapping cone of this map. Yes.
Yeah.
Attaching an ordinary cell to Q of A. So if I give you an A that's built from nothing or from the unit by attaching cells, then you can read off what Q of A is. Whenever you attach an E infinity cell to A, you just attach an ordinary cell to Q of A. The thing is, of course, that most objects are not given to you that way. But on ones that are, you can in principle use this.
Is there a good way to think about what it means, an E infinity cell, what this thing means?
I mean, you can write, again, I would encourage you not to, but you can write down a literal model for what it is, where you attach an ordinary cell, and then of course that has a partially defined multiplication. The old element, you know how to multiply them, but you don't know how to multiply the new element with the old ones, so you freely adjoin all multiplications of the new element with the old ones, and then you freely adjoin all relations that should be forced by the old multiplications, and then you carry on going. So there's a big construction, but it's a literal chain complex. It's not vaguely defined, but it's not very useful, I think.
So, sorry, so I should really not think about it as a short exact sequence, but as a mapping cone, because I just get, instead of taking something out, I put something in a higher degree.
For example, I could have started with the class X, the zero homology class.
Yeah.
So killing the zero homology class just means attaching a new cycle in degree 1 degree higher.
But like, even if it's not zero, I just attach a new cycle in one higher degree.
You attach a new
cell
element in 1 higher degree, it won't typically be a cycle. D of it will be
Yeah.
Yeah. So, something that Sander, Songaledges, and I proved is that for example, in a quite general situation, but in particular in the setting that I'm talking about here, this arrow is reversible. So if I know how to build Q of A by attaching it as an ordinary chain complex, then I can build A by whenever I see an ordinary cell for Q of A, I attach an E infinity cell for A. So I wanted to write that in some. So the converse is true. What that means is that if I define the E infinity homology of A, and what that just means is the ordinary homology of this QA object. If this, how do I want to say it? A can be obtained from the trivial algebra by attaching exactly the dimension over K of these whatever the dimensions of these are, I can attach exactly that many n comma d. Okay. So this is highly parallel to what happens in ordinary algebraic topology. If I have a simply connected space, and I look at its homology, I can always find a cell structure that whenever I see a z in the homology, I attach a cell. And whenever I see a z mod k, I attach two cells, one to make a z and one to make a mod k. So you can always find a so-called minimal cell structure, meaning it has the smallest number of cells that can possibly generate that homology. Okay? And this is not some fancy elaborate, this is like in Hatcher. Okay? There's a section called minimal cell structures. And the proof is basically the same proof as in Hatcher. Namely that you use something like the Horevich theorem. In this case, you prove the Horevich theorem, except that in this land, homology plays the role of homotopy groups, and E-infinity homology plays the role of homology in algebra. So whenever I have a map of E-infinity algebras, I can compare the relative homology of the objects and the relative E-infinity homology, and you prove exactly what the Horevich theorem would say, that in the lowest degree where this is not zero, this is an isomorphism. That's obviously not the proof, it's one ingredient of the proof. But given that ingredient, then you proceed just like you would do with topological spaces, basically. So what that means is that, of course, here's one application. Suppose you give me something built cellularly. You explain to me how to attach maps and so on to build it. Then I can compute Q of that object by playing this game. And maybe you've attached cells that somehow one of them seem to cancel the other one from the point of view of this chain complexity. So they, as a pair, they don't contribute to the homology. Then, by this principle, I can make a smaller cell structure that doesn't involve those two cells, because you somehow, the cell structure you provided me somehow was a bit redundant. Okay. But again, that's not really how we want to use it, because nothing that we're interested in is presented to us as a cellular object. What time did I, do you remember?
A couple of minutes.
Okay, let me just say the denouement of this. So, so for a given A, understanding this E-infinity homology tells us how, in principle, to construct A using E-infinity cells. So I want to use this, and that's going to be the point of the next talk. I want to use it on this specific E-infinity algebra. So I want to somehow access this E-infinity homology and then deduce something about a cell structure rather than the other way around. But for that, so we need another way of accessing Q of A. Because this way, this abstractly defined way is fine for abstractly defined things, but for a concrete thing, we need some other way to compute it, okay? And that's the goal of the next talk, is to explain a more down-to-earth thing that will compute these E-infinity homology groups. And there we will see things like Steinberg modules and things of that flavor show up. Okay, thank you.
Do one question now, and then we have a break until 11:30, during which you can ask more questions.
It's a little bit confused because typically when you take homotopy indecomposables of any operand algebra, you cannot recover the original algebra just from knowledge of, let's say, the vector space.
Right.
The homology without further algebraic structure.
Yes, so this is slightly bombastic what I'm saying here. All I'm saying is it tells you the dimensions of the cells. Of course, it doesn't actually tell you how to attach them to each other.
Ah, okay, so it doesn't give back A as an infinity algebra.
No, you would need to record much stronger. You would need to record some co-Lie structure of the actual object, yeah.
Okay, coffee time.